Okay, welcome. This note is on the topic of simple harmonic motion, which I guess I could say this to make you feel better. You might find the lesson difficult, but from an application point of view, from what you actually end up seeing in grade 12 university prep physics, it's pretty easy. Okay? The long story short, and I'll give you the short story long afterwards, but the long story short is simple harmonic motion assumes no friction. And that's it. Okay? You have a system where you assume no friction, which is what we do anyway. But we give it a special name, simple harmonic motion. And it has really important practicalities. And excuse me. And I'll show you some of the development, which is all, quite frankly, quite difficult to understand. I'll give you that. But if you want to understand it better, I really suggest you, after the video, you could look up some of your own videos on it or read. You can ask me for the textbook and read the textbook on it. But on the other hand, if you don't really care, it's long story short is that it's pretty easy. And by the way, I love this animation because this says that you got a vertical spring, and it's just saying, well, what kind of energies do you have, right? Well, the total energy is constant, and that is the heart. That's a crux of simple harmonic motion. Constant total energy, okay? And then if you look at here, at any point in time in the motion of the spring, like the gravitational potential when it's at the very top is a maximum, and at the very bottom, it just follows the height of the spring, right? The elastic potential energy at the very bottom is a maximum, and at the very top is 0, because this is like that last example we did, where it starts at x equals 0. And then the kinetic energy finds its maximum right in the middle here, which not directly in the middle, shouldn't be necessarily, but it's at the stretched equilibrium. So this is an awesome little bit, but it applies to simple harmonic motion because this bit here, the green right here, this keeps going on forever. In any real one, if I take a spring and I stretch it and it starts going, eventually it'll stop, right? Simple harmonic motion assumes it'll never stop. Okay, and the definition is periodic motion, where the acceleration is directly proportional to displacement. And what that just means is it never changes. Okay. Notice I have a picture of a pendulum here. Something I feel like I really rip you off of in my class is we never do any pendulums and pendulum examples. And part of it's just not that, it feels like you should do it, but there's no really good labs with pendulums, unfortunately. But an example of simple harmonic motion would be a pendulum swinging back and forth forever. It's a periodic motion, right? We're dealing with springs. That's where our focus is in the course. But it's anything that just keeps going on forever, and like I say, a pendulum would be an example. So simple harmonic motion models a sine wave in that, if you took amplitude to be height, amplitude being the motion of the spring itself, right, how high up or how high down it goes, right? Imagine this thing was going periodically between here and here forever, right? Well, the amplitude would be the distance from the center point, just like a sine wave. And we call period, which is the time it takes for a full cycle, just like in uniform circular motion. The period is the length of time from it to go. So imagine this thing goes all the way up, then all the way back down, and all the way here. Well, the period would be the length of time. Okay? And that's, if you had simple harmonic motion, it would look like a sine wave forever, right? Yeah, I talked to you about this. In problems involving springs or pendulums, we always assume an ideal. We use the term ideal spring to say that we never lose energy over time. So we always pretend it's simple harmonic motion. That's why the long story short is just treat it like you treat everything else. But it is important to get the idea and understand it. So for example, a not ideal, I told you that, here's a sine curve. Imagine this was our spring, right? Just like I showed you a couple slides back. It would go like this forever. Well, in real life, that doesn't happen. Over time, depending on how good the spring is, eventually, we call this dampened. So the term for this, and this is something you should know, right? The term is dampened. Any real system slows down with time. And I'm actually pretty sure that in your functions class I know Mr. Estel's asked me for some stuff to play with that he can show you dampened motion very specifically. So simple harmonic motion you study, not just in physics. So some special terms that we use that we wouldn't necessarily use, like we call like an A for amplitude. Excuse me. In regular, we're dealing with this exact example. We wouldn't call it A, we'd call it X for stretch, right? We say X equals, but if you're talking about simple harmonic motion, you'll see the term amplitude, which just refers to how much the spring has been stretched or compressed. And the idea that in simple harmonic motion, if you stretch a spring, it'll go back and forth from minus A to plus A forever. Okay? They'll go down to here, and it's using plus A, assuming that down is the positive direction. Again, not a detail you need to concern yourself with at all, just the basic understanding. And know that if you see A and you see the word amplitude, it refers to how much it's been stretched from the equilibrium position. Period, and we've used period before, time for a full cycle. So a pendulum, that would be all the way back and forth. And a spring would be where you release it till it gets back to where you released it. Okay, this is beautiful. This is the development of the formulas for simple harmonic motion. And because there are some special formulas, and probably you won't follow this very well because it's hard. It's hard. But let's do it anyway. Okay, imagine you've got, because we want to look at the formula that we're going to use for springs. Okay, so in a spring, we say, well, generally, spring is our net force on something is mass times acceleration. But in a spring, it's kx, right? So we've done this before. We'll say, well, mass times acceleration equals kx. So the net force on a spring is equal to kx. However, imagine this. This blue here refers to the motion of a spring, say, back and forth from its equilibrium point. So here's x equals 0, okay? And it moves side to side to side to side. And if I'm measuring sort of time for the full period or just for a small point in time, the speed of it would actually follow the exact same model as if it was a circle with radius equal to the amplitude. Okay? So the way that it moves, because this doesn't move, linearly, right? We know it's moving fastest right here in the middle. It's covering the biggest distance, or the biggest, well, I guess the biggest distance in the smallest time, right? It's going fastest here, and it slows down at the edges. And that really, it's hard to tell in this animation, but that's really what's happening. When something's moving in a circle, it would be the same. Again, forgive me, because I know it's hard. So, at the bottom is this is the short story long. Here's the long story short at the bottom. Here's the two formulas. But let me tell you why. Let's just go through it, okay? Centripetal acceleration, we know this formula with period in it, right? And we know this. The MAC then would be that times mass. But we're saying that the net force, which is centripetal force, if it's a circle, if we're treating it like a circle and the period to be in the same speed as a circle, right? That kx for our spring, again, picturing this as our spring, or object on a spring being pulled back and forth, okay? Kx is equal to all this. Well, we said x equals a for simple harmonic motion, and you end up with this formula. I want to solve for t. What I want to find is a formula for period of an object undergoing simple harmonic motion, okay? And I isolate t, and here it is. If I want to just rearrange that for f, flip it, right? So again, what I'm saying is, whoopsie. What I'm saying is, this blue represents a spring going back and forth. And its speed back and forth, it's the period, the measurement of period, the rate at which it moves exactly models a circle. And that's why we can do this, okay? And this just gives us a formula for period. So we've got, this is what you want. Circle this, put those on your formula sheet, and don't forget them. Okay, so as I said earlier, and I kind of talked about this already, but imagine I had, and this is a nice, but unfortunately this graphic here only refers to a horizontal spring because I don't have gravitational potential. But imagine I had a spring moving side to side in simple harmonic motion, and I graphed the energy with displacement. And I have R's, but imagine those were A's. So the total energy, right, would stay constant. The elastic potential energy would be, it would go from when it's most stretched, and then to no stretch would be 0, And actually they're mirrors of each other, right? So the speed, as the speed goes, the elastic potential energy does the opposite. Okay? And I have some good clicker questions on this next day. Okay, so that's the little video. Let's look at a couple examples related to simple harmonic motion. Here we go. So here's my little example of, Here's my little example of a mass that's moving from one end to another in simple harmonic motion. It's going to go forever. When the mass is displaced 8.5 centimeters and then released, it undergoes. So the force constant we know to be 140. So here's our information. Okay, it's never gonna go beyond A. That's the biggest it's going to be. That's its amplitude. And I want to know how far does it move in the first 5 cycles. So this should be very, very simple. It's just saying that, well, first of all, to solve this, I say, well, in one cycle, it moves a total of 34 centimeters. The reason is it starts here, right? And then it travels 17 centimeters to get to here, and another 17 centimeters back. So if one cycle is 34 centimeters, then in the first 5 cycles, it travels 170. Simply. That's all there is to it. And then B says, what's the period? Well, don't get your clock out, though I don't think this is done to scale. To do that, you use the period formula. Okay, this is the formula you need to keep on your sheet. Okay, so 2 pi times the mass of it. And again, we're not including the spring itself. We're just talking about the mass at the end. And K underneath. Okay, so to find the period, you just use that formula, solve, and you get an answer in seconds. Okay, 0.27 seconds. Definitely this isn't drawn right because the period on this thing is way slower, but my computer might be slowing down as well. With lots going on the computer today. Okay, very simple. So like I said, with simple harmonic motion, understanding the development of the formulas is one story. If you really want to, I encourage you to go ahead, look it up on the net. It'll go through a nice development, or borrow the textbook, but you know, you can do just fine in grade 12 physics as long as you can do all this stuff. Okay, all right. Another example, here I'm given a mass and I'm given a frequency and I want to find F. That's all. Okay, so you're given the formula that you know, force constant, sorry, we want to find K, I'm sorry. So we're given the mass, we're given F, we want to find K. This is the formula on simple harmonic motion. Solving for K to get K by itself. So this is just, really this question is just a rearranging question, right? So I go multiply both sides by 2 pi, square both sides to get rid of the square root symbol here, right? And then I have multiply both sides by m, sub in the numbers, and with a number with newtons per meter, and that's a pretty regular number we would use, about 25 newtons per meter. Okay, so that's applications of simple harmonic motion. Like I said, the short story long is pretty hard, but the long story short isn't. That's it.